for the audience, and this is the second talk of this session, and the Declarative Solutions. And the title is Decomposition-based Job Shop Scheduling with Constrained Clustering Remote. I'm sorry, clustering. Remote is constrained clustering, of course, sorry. The talk will be given by Martin Gebser. And Martin, the stage is yours. You have 20 minutes.
Thank you, Francesco. Do you see my slides well?
Perfectly. We see your screen.
Thank you. Because I don't see you. Thank you, and that's all new to me. Yeah, I'm Martin. Welcome, and thanks for the introduction. And right from the beginning, I have to excuse, I'm jumping in for my colleague Mohammed, El-Kholany. This is joint work with Mohammed and Konstantin Schekotihin. And actually, Mohammed did most of the work, but we are, for obvious or apparent reasons, still in home office, and he has internet problems, and I'm just jumping in, and I hope to tell you well what basically his work was. So he is a PhD student, and that is one of his main topics, which he is working on: job shop scheduling and decomposition, actually. And let's have a look together. What is this about? Probably many of you heard from the basically classical job shop scheduling problem, and what we look at here are basically the standard versions, basically the hard combinatorial benchmarks, but there are many applications, of course, in practice as well for particular versions. Here we go for the classical setup, just to have somehow instances ready and something to work with. And pretty soon, job shop scheduling gets quite complicated, at least the optimization versions of it. So it's necessary for search and optimization to produce good results, to decompose and somehow go to sub-problems. And this is meant with iterative JSP solving, job shop scheduling, problem solving. I will talk about this. And the question that arises there is then how to decompose large instances of the problem, how to do that well. And this is the third bullet I will come to, and then I will present experimental results and conclude with the talk. I hope I don't need to convince you that scheduling arises nowadays in many settings in industry. For instance, I can say we have Infineon close here at Villach, which is in Austria in the south, and they have a large factory with thousands of employees. And for instance, when they show us records of their production, you can see, there are 50,000, 100,000, something in between operations per day performed. And as we all know, also there are quite some capacity problems recently in industry because of the logistics and all the scheduling. It's so complicated. And of course, there is a desire to improve in that field, and that has quite some relevance. And that's why we are looking at it. Okay, there's also some illustration here. There are many real-world settings nowadays where one would like to use smart techniques to schedule nicely and use resources efficiently. That's the basic topic underneath in all of these applications. And if we do, for some reason, the graphics show up late. If we look at this, in the most simple classical setting, and I hope you see my mouse pointer here, in this easy setup, you can say,
Martin, I don't know whether it is intended, but we still see your first slide.
Then this doesn't work as I want.
Maybe you have to switch screens, I don't know.
Yep, sorry for that. I have no clue why. Then I go.
Yes, now we see your mouse. Now we see.
Now you see my menu. Okay. Sorry, I don't know what the full screen does. I hope it's okay.
No. Yes.
Yes. In this classical job shop scheduling scenario, it's pretty simplified version, say, and what one gets is sequences of operations that need to be performed. These are called jobs. For instance, here in this example, what we use in this job 2, we have 3 operations to perform. They are ordered from left to right, and we always get a machine directly assigned that has to do the operation. So for the second job, somehow the first operation goes to machine 2, then 1 and 3. And we also get operation times, like here it's time 1. The second operation takes 4 time units and again 4. And we can have any number of jobs like this. And for simplicity, each job uses each machine in some order for some operation and for a given time. And then we can make a schedule, which you see here on the left. And here we see in blue, for instance, our second job, the first operation, second one, and here is the third one. And the machines also have quite a strict capacity limit. Just one operation can run there at a time. And so we need to wait for machines to get free before we can perform the operations. And at some point, the jobs get completed. And what we look at as one of the possible optimization targets, there are several versions of the problem, is how long does it take to schedule all of these operations? And in this example, which is here for illustration, there's a time point 14. If one goes through and checks how many time units does it take, we need 14 time units to finish the last operation that we have among all of the jobs. And this measure is called makespan, and that's the version we go for in our work. And we want to have this as small as possible. I didn't check, but I guess that this might be an optimal schedule for the instance. And if we then go on and look at what is actually inside this problem, one can imagine this as another view on that as a graph with 2 kinds of edges. And what you see here, these basically there are 4 sequences. These indicate the jobs, and they must be performed in order, so we cannot alternate the operations of a job. That's sequences that are basically static and given. And between the operations, also some processing time needs to elapse to perform the operations. And what makes it highly combinatorial are these dashed disjunctive arcs, and they connect the operations that run or need to be performed by the same machine, and those compete basically for a resource. And there we also have to decide on an order. So permutations play a role, and that's quite heavily combinatorial what we get here. And to control to some extent the complexity for the optimization and how long will it take to schedule things nicely with an optimization technique, like for instance answer set programming. That's what we used. It's advantages or necessary, say, to decompose the problem and split the operations in the full problem into smaller portions. And our approach to enable iterative solving and make sure that we don't deal with too many operations at once that one cannot handle anymore. The idea is, basically clustering plays a role later, that we separate the operations and say there's a bunch of operations you see here on the left that will be scheduled first and basically optimized so that the time to complete the operations you see here is as little as possible, and then we go on and extend to the second portion of operations, which you see here on the right. And this makes it controllable to some extent. How long will it take to arrange the operations in each cluster? And what one needs to be careful about, what you see here, is that beforehand we had a lot of disjunctive arcs, and These are now reduced. Yeah, that's a complexity reduction. That's nice. But if the clustering is bad, that we choose a bad order, in the optimum, if this operation here, the second operation of the second job, is performed after the second operation of the first job, we have done a bad decision, and then we get suboptimal results. So what one would like to have is that these clusters are done nicely, in the best case perfectly, so that one basically follows the order of an optimal schedule. But of course we don't know what is optimal and what not, and we have to make good decisions here. This is the problem. Once we have done this with the clustering, just at the intuitive level, just to show that roughly what then happens, we can then take the operations of a first cluster. We say we schedule them as good as we can to minimize the make span, and then we can go on like this for another range of portion of the operations. And then, what simplifies it is then the first part of the schedule is fixed, and we schedule what comes in addition, and so on, as often as we want or need. And at the end, we see our final schedule, and the hope is that the clustering was done well, and that basically the local optimization also comes close to some globally optimal schedule. Then it would be the perfect situation, and the problem is how to get there. And in our work, to somehow the baseline that we used is just take some simple static features and order the operations by this, and then say, partition at some point. Say we have 1,000 operations, we have a simple measure how to make a total order, and then we say make 10 portions of the problem. So we take then bunches of the first 100, second 100, third 100 operations. That would be easy to do, but taking some arbitrary static property is a bit problematic. And here the idea is just to take those features of the problem basically associated with the operations, and later on try to do something smart, clustering instead of some arbitrary simple feature. And what we used in our work, so there's literature on that, so these features have been considered by others as well, so that's not particularly novel. One can say, what I directly get from the problem definition is the processing time for each of the operations. That's surely a feature I get directly from the problem. If I want to have more interesting features, what is often relevant or inspected is the earliest starting time. And it's still a static feature and pretty simple. If you look at it, it's basically the sum of processing times following the job order of predecessors. So at the beginning, for the first operations of each job, it is 0. Then we proceed, and what we collect is then the processing time of the predecessor operation, the direct predecessor operation, and then we can go on and sum it together. And what we get in the end is a measure that roughly estimates when will it be possible to launch each of the operations. And in the best case, if you only would have one job and all machines are free, you would get these as the best possible starting times. That's one static feature. What is also inspected quite frequently when people look at scheduling problems is the remaining processing time, which somehow looks into the future and estimates or says how much work still needs to be done after an operation. So at the beginning, it's the entire processing time for all of the operations in the job. For instance, here you see it's 17 for the first job. It has 3 operations, and that's the sum of processing times. And then it reduces, again, from left to right. And here we have already finished predecessor operations and look how much time is still remaining to completion of each of the jobs. And at the end, you just have the last operation. That's it. And this can be used to decide, how much work do I still need for one of these when I do these operations. So how important is it to do it early that I can finish the job still in a good time in the end. That's the idea. And there's one more we looked at, because that's also common to look from the perspective of resources. So how important is a machine, or how critical is that? And to do this, one can say, okay, we just what you see here are the earliest starting times again. They have been calculated as shown before, and then I order my operations per machine, and I assume from left to right is the execution order of these operations, and then I can say, okay, when this machine is somehow like this one, this operation is there and needs to be executed, its machine load is the entire sum of operations that want to run on this machine. And then we say, okay, we go again in this order, and the machine load then successively reduces, and we attribute the work that still remains on each machine to each of the operations. We have another measure, okay, that's what we can do in addition. That's the resource view. And what is maybe the most interesting is if we say, let's take greedy heuristics and scheduling algorithms, say, that want to approximate good solutions, and use those instead of just some static numbers that we associate. And one of those heuristics is, for instance, FIFO, where we say, okay, the first job that is, first operation that is ready to use a machine gets it as soon as the machine is free. That's a simple, greedy scheduling algorithm. And in this example, we just take the first operations for all of the jobs. We are lucky that they use different machines, so their starting times is 0, and they don't need to wait. And then we can continue to schedule the next operations of each of those jobs. And what might be interesting to see here, this second operation of this guy here, the second operation of the second job needs to wait for its machine to get free. So there is a gap to its predecessor, and this is also an attribute that is important in scheduling. How long does the operation wait idle to be scheduled? Because idle means that there is some gap here in the schedule, and probably that's not good for minimizing the make span. So one should critically look at this, and this is a feature we get also as a side product of the greedy algorithm. Here's again a gap of 2. We have it here, and we see a starting time and the waiting time. I need to rush up. So these are basically the features we look at. So a bunch of static features, and then also these dynamic features like starting time and waiting time from some greedy algorithm, and we used several actually, and this was one example, this FIFO. And here we see this, and in addition to FIFO, we used greedy algorithms with most total work remaining, is what this should indicate, and earliest starting time for the operations as the criterion, what to schedule next, greedy criterion, and then our static features and waiting times. So in total, from all of these features we looked at, we more or less said the greedy algorithms are very informative, so we always want the starting times, and the other features we can add as we want, and we get combinations, and 16 possible combinations we investigated in the experiments. Because it's not straightforward to tell which is now the best feature set to use. roughly the clustering algorithm now, normally one would now say, okay, take the features and do something like nearest neighbor. The problem is that we need to go in the order of execution. Yeah? If our clusters violate the job sequence, then we cannot schedule it properly, and it gets infeasible. So what we do here to keep the order is to say, first of all, the user provides a number of clusters, and yeah, we evenly want to split the problem, and so the total number of operations divided by the number of clusters gives the capacity, how many operations we would like to have per cluster. And then it goes into the data mining and clustering directions. Yeah, basically there is a random choice of initial centroids, so how to arrange a cluster. And this is somehow where it gets non-deterministic to some extent what we get. And then we go and fill up these clusters. So we check, are there clusters which are not yet populated, or have we already assigned all operations? If not, and the cluster capacity is not exceeded, then we see how far is the nearest operation from the centroid, and we take it together with predecessor operations, possibly, to make sure that we don't violate the sequential order of the jobs. And we do this as long as the cluster still has capacity left and we want to put something in. And if we see now it's large enough, the portion of the problem we want to have is there, we proceed to the next cluster. And also the centroid is updated to somehow try to get us similar operations into each cluster. Okay, and from our benchmarks, I need to be a bit short on that. What we selected hard benchmarks, which are difficult for greedy algorithms, at least, that there is room for optimization. And we use here as baseline just greedy algorithms, FIFO and most total work remaining, and you can see they are pretty good. Yeah, this green and blue line, and what you see here in yellow and red is single and multi-shot solving with a simple static criterion with ASP, and we see that we don't even manage to beat these greedy algorithms, and then we use the clustering and basically the best version that we have, and here we see that we are close or often also better, so we get into the direction of these greedy algorithms, maybe not making a big advantage because the scheduling problems are still hard and we don't know whether our clustering is perfect. And on another class of instances where it's also difficult, here we see kind of, it really depends also on the instances, whether greedy approach.
Martin, sorry to interrupt you, but you're running out of time. So
okay.
you can conclude, but I don't know how much time it will be left.
1 minute. I stop on this slide. Okay,
let's go on. So sorry for interrupting you. Okay.
Yeah, you can see here in some of these instances the greedy algorithms perform very well, but here they are sort of in trouble. These instances are from the literature. We didn't create them ourselves to produce that. And here we really get some advantage. And also with the clustering, and you see that the single shot solving goes to nowhere because it's just too combinatorial, and in the time we use, maybe it was 1 hour, I can't say exactly now, you can't get even close if you don't decompose. And thank you, and sorry, I didn't practice the talk, that was my problem. And we are finished.
Okay, thank you, Martin. So I didn't mean to disturb you, but we have some time constraints, so an additional 2 talks to deliver. So thank you very much for your talk. And are there any questions from the audience? Okay, in the meantime, so as far as if I understand correctly, Martin, so you propose this algorithm for the clustering, right? And the actual scheduling is performed by ASP. Is that right?
That's right. Okay, with different logic.
Okay, great. So the last 2 charts you showed us, and those are just two charts.
Yeah. Here.
Okay, so these are solution qualities. Okay.
Right.
And
Right.
what about time performances?
What we did, I think it was it 10 minutes or 1 hour? We used quite, or maybe 30 minutes, quite short time basically. And if we split into several clusters, then we use basically the total time is the same, no matter whether we do the entire problem or we split into the clusters. Then we use certain time slots, and then we optimize for the time we have, and then we take the best solution we got, and either proceed to the next cluster or say, this is it, this is how it works. So there's quite limited amount of time, and you go for the best version that you have, the best solution that you get in this time. And the greedy algorithms, of course, they are super quick. They you don't need the timeout. That's how it works. What we do.
Okay.
And we cannot optimize to the end on these problems. They are too large, so you always interrupt the optimization process at some point. It's even with the clustering. We just want to get close to a good solution in a short amount of time.
I see. Thank you very much. Any other questions from the audience? I see none. So let's